This recording is for Primary Math 6. We're working the challenging word problems pages 11 to 14. This is again in that first section about algebra, and these are the challenging problems in that section. And we just sort of jump into algebra this year, and then we go back and do other things we're more familiar with. But this section will be very different than what our kids have done before. And again, I would encourage you to do this section more with logic and concrete ideas than necessarily just showing algebra steps to solve it. They will begin to understand intuitively the algebra steps, and that of course is the goal. But first off, the very first problem we have says to find the value of n in the equation 5n minus 2 equals 2n plus 10. This requires us to, again, I would say, my opinion, the way to solve this would be to have scales like this and just show that right now they're balanced. 5n and 2 negatives is the same thing as 2 n's and 10 positives. When I work with positive negative numbers, I make the point that a minus 2 is the same thing as a negative 2. It works exactly the same. We get really hung up on what's a minus and what's a negative, and it really works to be the same. Here's the reason this helps. I have 5n minus 2, or 2 negatives, when I want to get n by itself, right? One thing we can help our kids understand is that a negative and a positive cancel each other out. So if I put 2 positives down here, effectively those go away. They become 0, just like a positive negative charge cancel each other out. And so when I want them balanced, I had to put 2 positives on this side so that I could get rid of these 2 negatives, and I had to add 2 positives to the other side so that it would be the same. You could certainly show your student that when we do that, a shortcut way of writing it, instead of necessarily drawing out the picture every time, is to point out the fact that we put 2 positives in on both sides, and you can see that it's balanced because I did the same thing to both sides, and that makes the negatives disappear on the left side. So now all I have on that left side of my my balance is 5n. On the right side, I now have 2n and 12. Then what do we do next? Well, I need to get rid of the n's, so I could do the same thing, put negative n's there. Or we can show another technique, same idea. Again, the goal here is to balance things. I can take away an n, 2 of them, and take away 2 n's on this side. Okay, so I'm just going to remove them. I could show removing them by subtraction if you want to show them the shortcut, but the idea is that 3 n's is the same thing as 12. And then if I have to take these 12 and put them into groups of, or into 3 groups, right, then we know what happens to that, right? There ends up being 4 n's, or 3 n's and 12 numbers, means we end up with 4 for each of them, right? Because I'm going to take those 12 and divide them into 3 equal groups, and that tells me that each n is equal to 4. We're not doing step-by-step algorithms so much as we are just showing what happens when you deal with things that are equal and you do something to one side and you have to keep it balanced on the other side. Number 2 gives us a problem and a hint. 52x minus 13y is 65. And we're trying to find the value of 28x minus 7y. And it gives us a hint. It tells us that 52x minus 13y is the same thing as 13 4x's minus y. All right, let's start by helping our children understand what that means. If I took all of these and I broke them down into 13 groups, if I had 14x minus y, there are 13 kids, and I gave every one of them 4x's and a negative y, and I did 13 times, since 13 times 4 is 40 and 12, or 52, then that's why we're showing this. 13 of these, if I have these 13 times, I would have 52x and 13 negative y's. All right, why is that helpful? Look what they're looking for here. They want to know what 7 times 4x minus y is. 4x minus y 7 times would give me 28 x's and 7 y's. Now, we're not talking necessarily about factoring, we're talking about division. We're trying to help our kids to see it intuitively. What if they don't? Okay, at this point, your child is going to get there and you're going to think, do they see it intuitively or do they not? I'm going to talk about that in the second class recording, and so I'll just save that whole conversation for that because not everybody's going to watch this recording from beginning to end. So here's the point. If 52 minus 13y is also the same thing as 13 4x minus y's, and that's equal to 65, then how many is each of these, right? 13 times what is 65? And probably that would be obvious enough that it would be 13 times 5. Or you can do a division problem to figure it out, which tells me that 5 is a nickname for 4x minus y. If this is equal to 5, then this value is equal to 35. I didn't have to solve x and y. Okay, I just have to recognize the correlation in all of these. So here's what we're saying. We're saying that 4x minus y is equal to 4. So if I have 2 of them, it's equal to 8. If I have 3 of them, it's equal to 12. If I have 13 of them, it would be equal to 65. And I started this whole thing by looking at the wrong number. It's not 4, it's 5. 4x minus y is equal to 5. And then 2 of them is equal to 10. And 3 of them is equal to 15. And 13 of them is equal to 65. And 7 of them is equal to 35. So number 2, the answer is 35. Number 3. This problem gives us the information that the figure below is made up of 2 squares. Now mine don't look like squares, but we're going to go with the fact that they are. And the total area for the 2 squares, both of them, is 136 square centimeters. And we're trying to find the value of x plus y. And so what we know is that if this side is x, then the area of this square is x times x, or x squared. If this side of the square is y, then the other side is y, and we have an area of y squared, and these would of course be in square centimeters, okay, because the area is length times width, or x times x. So I know that x squared plus y squared is equal to 136 square centimeters. Now in another class they might tell us something like, the more information. 1 is 3 more than the other, or the sum of the sides is something or other, and give us more information. We cannot do anything with this except for, really it's like going to end up being like a guess and check, like find something that works and prove that it, and answer the question of x plus y. Maybe it jumps out at you, if I'm thinking about perfect squares, that 136 is the same thing as 100 plus 36. And that is, again, we're looking to help our kids develop that intuitiveness. And so when they look at 136, I hope that they have this just natural tendency to go towards 100 is a perfect square and 36 is a perfect square. We've talked about 10 times 10, 6 times 6 enough times for them to see that. But that's what we want to do, is pull out that intuitive side of them. That would tell us that x is 10. It would tell us that y is 6. Does x have to be 10 and y have to be 6? No. As a matter of fact, it would look better if you said x is 6 and y is 10. It could be either way, right? It doesn't necessarily have to be a whole number. We could, if we were at a different grade level, use calculators and come up with some approximations or some values that it could be. It may not be that. However, these values, either of these values, option A, option B, both meet all the criteria given to me. There are two squares, total area is 136 square centimeters. All I'm being asked to find is the value of x plus y. And so if that's 10 plus 6 for 16, or 6 plus 10 is also 16, and those both work. The value of x plus y is equal to the number 16. And on this one, it doesn't have units because it doesn't have units. It's just a number. What is the value of x plus y? That's a number. The number you're looking for is 16. Number 4. The first part of number 4 asks you to draw the next figure. So figure 5 would look like this. It's going to have, and this would be good for your child to be able to verbalize, each of these figures has one middle square, and then there are a number of squares going out to the side. It's the same number on each side in all 4 directions, just straight out, north, south, west, and east, if you will. And notice that since it's figure 5, what we have is 5 minus 1, or 4 squares going out. And that works for each one. On the third figure, you have 3 minus 1, or 2 squares going out. So this is the next figure. That's fairly easy. Part B asks us to find this answer. How many cubes are needed for the 7th figure? What about the 12th figure? How do you find the value of those? Well, again, look at what we have here. For the 7th figure, you're going to have 1 square in the middle, and then you're going to have 6 going out to the top, bottom, left, and right. So you're going to have 4 sixes, 6 times 4, 4 times 6, going out. And that means 1 in the middle plus the 24, or there will be 25 going out from the center. What about the 12th figure? You still have the 1 in the center, but this time you have 4 times that the number 11 is represented. 11 squares going out. You're the 12th figure, so it's 11 squares going out from the center. So 1 plus 44 is 45. Then look at C. C basically says, okay, you've done some practice. Now tell me, what do you do for the nth term? So for the nth term, we're going to take the number 1. We're going to add to that n minus 1 times 4, and that's going to give us the number of squares it'll take to build the figure. Now the use of parentheses is of course somewhat new for us. The idea is that we want to do 4 times all of this, and then it doesn't hurt to go ahead and talk through the process of simplifying it. If you have 1 plus, if you have n minus 1 4 times, right, that's n minus 1, n minus 1, n minus 1, n minus 1. That's what we mean by n minus 1 times 4. Altogether, that's 4n minus 4. And when I put that together, I have 4n and 3 negatives. And so it all comes together like that. And that's the answer in terms of n. Number 5. This problem tells us that there are X candies in a bag. That's a total. We know that Jane took some candies. Ruth took twice as many candies as Jane, and Sally took 25 more candies than Jane, and the bag is now empty. So I drew a picture, and I used the letter S for some because Jane took some candies, and then Ruth took twice as many candies as Jane, so she took some candies twice. And then Sally took 25 more than Jane, so she took some, and then she took 25 more, and then the bag was empty. And so the question that we were asked first is to express the number of candies that Jane took in terms of X. So again, if you're taking the number of candies Jane took, that's S, in terms of X, then I want S equals blah, 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 X by itself on the other side. Okay, the X is the only variable, S is totally alone, the other side has X and whatever else I have to have. So this is the idea. First we need to get to this point of having an idea. Then I drew a picture like this. This shows that Jane's plus Ruth, and add in there Sally, and those candies all together were the entire bag, because when they were gone, the bag was empty. Therefore we have a balance thing there. But what I'm trying to get here is S all by itself. So again, with the concrete idea of a balance, if I take 25 off of this side and take 25 off of this side, it is still balanced. All right? In order to be balanced, if I take some off of this side, I have to take some off of the other side. Now the fact that it's now X minus 25, right, that's okay. And the problem is that these are 4 S's. So I could say 4S, just to make it simpler, 4S balances that. So what is 1S? Well, that's easy, right? 1S would be if you took X minus 25 and you divided it into 4 equal parts. Again, we're really working to stick with some logic and some concrete information here and not get too hung up on the algorithms and the steps. Make it very, very logical and concrete. Number 6. This problem gives us a chart with all the items and all the cost, and it starts out very concrete and asks us to find the cost of each of the following. If you have 2 cups of tea, that's going to be 2 times 80 cents. And the egg sandwiches, if you have 2 egg sandwiches, it's going to be 2 times $1.20. Now 2 80 cents, 8 tens doubled is 16 tens, that's $1.60. 2 times $1.20 is $2.40. Altogether, I'm going to have $4 for the charge of that order. So setting it up where you have room to write a little bit and show the work a little bit. If you have 2 coffee, it's 2 times 90 cents. That's $1.80. 1 tea is another 80 cents. 2 tuna sandwiches is $2.60. 1 egg sandwich is $1.20. Can we practice some mental math here? Right? We have a 20 and an 80, that's $1, and an 8 and a 6 is another $1. So I have 2 extra dollars. That makes $6 total. And once I took this 20 cents out, I have 40 cents left, and so $6.40 would be the cost of order B. Now all of a sudden in order C we jump to variables, MTs instead of 2 T's. And so if T is 80 cents and you have M of them, you do the same thing. Instead of 2 times 80 cents, I'm going to do M times 80 cents. And for coffee, instead of whatever, 1 or 2 coffees, whatever, I'm going to do N times an amount of coffee. 90 cents times N. And so the total amount here, we can't come up with an actual number because we don't really know how much you spend on tea or how much you spend on coffee, but this is what we call an expression. I'm going to draw through the middle of it. This is what we call an expression that tells me how much I spent on this order if only I knew how much money was spent on tea and how much money was spent on coffee. Egg sandwiches and tuna. If an egg sandwich is $1.20, then I have 1.2p. A tuna sandwich is $1.30. So this is going to be, again, written as an expression, 1.20p plus 1.30q. If your child asks, do you have to put the 0 at the end? You really don't. Because it's dollars, we always do. because we don't talk about $1.3, we talk about $1.30, right? And so, and I really should have dollar signs on every one of these, did for a while. These are also going to have dollar signs as part of their units. Okay, and then the last one is the same thing, it's just a lot longer. This is 0.8A. I'll just put the plus sign here, plus the coffee is going to be 0.9B. You don't have to put the 0, you can put the 0. For the sake of space here, I'm not putting 0, plus 1.2C plus 1.3D. And you can't combine them, you can't put anything else together. That is the answer that they're looking for, except of course it'd be, I don't know if you have to have dollar signs in the expression because it's going to be part of the answer. But anyway, just keep in mind what these numbers mean. It's because T is 80 cents that we did 0.8 T. Number 7. This problem gives us a lot of information. We're told first that shop P has 210 television sets. So I just drew a bar and I'm calling that 210 long, or 210 television sets. Now it, referring to P has Y fewer television sets than shop Q. Turn that around. Q has Y more than shop P. So we have P and we have Q, and Q has Y more. So that's what I drew. And then Q has 1/3 as many as shop R. Again, turn it around. That means R has 3 times as many as shop Q. So it's the other way around, right? Q is 1/3 as many, so R has more. How many more? 3 times more. So I have 3 210s and 3 Ys, and that's how I can draw and get a good visual, concrete understanding of shop P, Q, and R. First question, how many more television sets does shop R have than shop P? Well, what does P have? P has this. So that's the same. Everything else is more. How many more does R have? Well, it has that 210 and that 210 and all of these Ys. So letter A, the answer is simply going to be 420. That's 210 plus 210. Add 3Y. Part B asks a question, if Y is 110, how many do the 3 shops have in all? All right, well, I have 210, and we could do it this way. I have 1, 2, 3, 4, 5 of those. And in addition to that, I have Y, which is 110. 1, 2, 3, 4 of those. 5 200s is 1,000, so that's 1,050. 4 hundreds and 4 tens is 440. When I combine those, I get 1,490 television sets if the value of Y is 110. Let's look at number 8. This problem tells us that there are W lampposts on the road, and the distance between each lamppost is 20 feet. There's a lamppost at the beginning and a lamppost at the end of the road, and we're supposed to express the length of the road in terms of W. So if you have W lampposts that are each 20 feet apart, how long is the road? That's what we're trying to find out. The key here, and we've done it since early on, primary 1, we started doing this kind of thing, is to realize that there's one 20-foot jump, and that counts for the first and second lamppost. If the road was only 60 feet long, that would be 4 lampposts. Change color so we can see that. First lamppost, second, third, and fourth. The temptation is to say that the length is equal to 20 times W. However many lampposts there are, multiply it by 20. The reason it doesn't work is because the first lamppost doesn't have a 20-foot attached to it. You have to jump 20 foot to get to the second one. So just like we've always done in Singapore math, when you count the first one and the last one, you've got to be careful. And I would suggest you break it down into smaller parts. When you have 4 posts, when W is equal to 4, your length is equal to 60 feet. You could do a few of those. What you would find is that you have to take the W and subtract 1 from it and multiply that number by 20. It's not 20 times W, it's 20 times W minus 1, because this one does not have a 20-foot bounce, if you will, to count for the length. The first one doesn't have 20 feet attached to it. The number of 20 feet jumps is however many light posts you have minus 1. So then another way to write that, if you have W minus 1, W minus 1, W minus 1 20 times, what you have are 20 W's and subtract 20. So that is how we think through number 8. Number 9. This problem says that there are 30 strips of paper, each with a length of X. Each strip overlaps with the end of another strip by 2 centimeters, and they're all glued together to form one long strip. And we're trying to express the length of the longer strip in terms of X. So this we have them separated as if they're on separate levels, but really what we have here is one long strip of paper that is 30 pieces of paper glued together, and we're trying to figure out how long is this from beginning to end. And again, this is not 30, this is just a small subset of it. There are a few ways to do this, and it's really, I think, a great place to stop and pause and spend a little time with your kids. Really the way the book has it set up for you to do is to realize that this distance is X, and then if I just looked at this part of it is X minus 2. And since I've gone to this line here, I just have to do this part of it, and I have X minus 2. And each of these is going to be X minus 2, because this first 2 on this line are gone, and the first 2 on this line are gone, the first 2 on this line are gone. This first X, I have the whole thing. And notice, if you went here, 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 I'm covering the whole thing with no overlap. Okay, so if the first strip is X, and then I have 29 other strips, and all of those are X minus 2, 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 right? That is 29 X's, and you would end up subtracting 58. I actually just looked in the back, and they actually give this with units of centimeters as a final answer, and that's fine. It doesn't hurt to change it to 30x minus 58 centimeters just by saying 29 of those ends up being 30 minus 58. You could also, I think it's interesting, to stop and realize that you could do this by saying, you know, the top of these, the first, third, fifth, seventh, ninth, all of those have a length of X, and the ones underneath, pretend like those are the same length, without those two and without these two, it's X minus 4. So all of these distances are X minus 4. And then what happens on the end, right? On the very end of this, the very last one is going to end up being X minus 2. And if you think about it a second, the 2 on this side will disappear, but it doesn't have one up here to cause this part to go away. And again, this is a nice, lovely, awesome way to do it. I think it'd be wonderful if your child has the bandwidth to look at it with you and think, oh, look at that. I'm going to have 15 of these. I'm going to have 14 of those. And that very last one, it's always good to look at the very last one and see what it does, is going to be X minus 2, because this end point doesn't get covered up by another top one. And so if you work on this one and simplify it, 15x and 14x, and you're going to have a subtraction of 40 and 16, which is 56. Then there's one more x, and there's two more to take away. Guess what we have? Putting them together, 15, 29, that's 30x. And then we have the 56 negatives, and the 2 negatives is 58 negatives. And that is how many centimeters we have for an answer. Again, do you have to do it two ways? No. If your child has the ability to stop and think with you about it and kind of go through that, I think it's a great little extension to see that you can do it a couple of different ways, and how you divide it up works no matter which way you accomplish it. Last problem for this section, number 10. According to this one, an apple costs P cents, an orange costs Q cents more than an apple. What is the total cost of 2 apples and 3 oranges? And so I drew it like this, very simple, just help me organize my thoughts. 2 apples, 3 oranges. If I have 2 apples and 3 oranges, I'm going to have 5P. And if I have 2 apples and 3 oranges, I'm going to have 3Q. And so 5P plus 3Q cents, our unit is cents, all of these are in cents, that is the cost of 2 apples and 3 oranges. And certainly you could write that a few ways, right? 2 apples and 3 oranges. And you could see how I end up with 5P and 3Q from that. You could write it like this. Where you have 2P and 3P plus Q, which is 2P plus 3P plus 3Q, and 5P plus 3Q. Notice we didn't go into any rules about like variables and adding like terms. We're doing it very intuitively and seeing that 2 of these and 3 of these is going to end up being 5P plus 3Q cents. All right, that is the end of this recording. Thank you very much.